Hello and welcome to another video in the series on partial fraction decompositions. In this video, we are going to examine whether or not reducing a proper rational function is actually necessary. Now, we have already seen that if the rational function is improper, the degree of the numerator is greater than the degree of the denominator or equal to the degree of the denominator, then we do have to perform a division process so that the degree of the numerator is strictly less than the degree of the denominator. So our objective for this particular video is just to demonstrate how partial fractions works with a proper fraction that is not reduced. So we're going to consider the following problem. Here we have x squared divided by the product of x times the quantity x squared minus 1. Now, if we recall, the degree of the numerator is 2, the degree of the denominator is 3, so we do have a proper fraction. And if we take the approach of using partial fractions, we'll go ahead and factor the denominator. We have x times the quantity x squared minus 1. That breaks apart into one denominator being x, one denominator being x minus 1, and one denominator being x plus 1. Because these denominators are linear in x, the numerators associated with these will all be constants. So we have a over x plus b over x minus 1 plus c over x plus 1. And that's going to be our template for our partial fraction decomposition. The next thing now is to determine the values of a, b, and c. So we go ahead and combine the fractions, and we end up with the system that 1 is equal to a plus b plus c, 0 is equal to b minus c, and 0 is also equal to negative a. And that is our system of equations that we need to solve. So we know that a has to be 0, and when we solve the system for b and c, we get that to be equal to 1/2 for b and 1/2 for c. So our decomposition of x squared divided by the quantity x times x squared minus 1 is going to be equal to 0 divided by x plus 1/2 divided by x minus 1 plus 1/2 divided by x plus 1. So what happened here was that the factor in the denominator that has a 0 as the numerator is actually the factor that could have been divided out or would have been removed in the reduction process. What this did is that it traded the work at the beginning to reduce the proper rational function to shifting that work to the end in order to solve a larger system of equations. While it is not necessarily incorrect to not reduce the rational function, it does result in an increase in the size of the system if you do not reduce your rational function down to lowest terms. So if we actually take a look at the same rational function, but this time reduce it first and then go ahead and perform the decomposition, we have that x squared divided by the quantity x times the quantity x squared minus 1. We can divide out x from both the numerator and denominator of this, and this will reduce the fraction down to simply x divided by x squared minus 1. We know that x squared minus 1 is the difference of squares, so we may rewrite that as x minus 1 times x plus 1. We use each of those distinct linear factors as denominators for our template for partial fractions. So we have a constant a divided by x minus 1 plus a constant b divided by x plus 1. And we're going to determine the values of a and b. We combine the fractions, match up the coefficients, and we end up with a plus b equaling 1. These happen to be the coefficients of the x variable. We also have as another equation on our system of a minus b, and that comes from the constants when we get done with combining the fractions and matching up numerator terms. And a minus b is going to be equal to 0. So our system is 1 is equal to a plus b, and 0 is equal to a minus b. And here we have a and b both equal 1/2, and we end up with the same decomposition. We have the rational function of x divided by x squared minus 1 is equal to 1/2 x plus 1 plus 1/2 divided by x minus 1. And these are the same, this is the same decomposition. The reduced form had a smaller system to solve. It was just a 2x2 instead of a 3x3 system. So if you do not reduce your fractions, your rational functions, and you proceed with the partial fraction decomposition, you may in fact get zeros as some of your values for the constants. And this is not anything to be worried about, in that the decomposition is telling you that you could have reduced your rational function because this factor was not necessary. So let's consider another example. Here we have x divided by the quantity x squared times the quantity x squared plus 1. This is an example of a rational function that's not in lowest terms, and if we proceed with the decomposition, we end up getting a over x plus b over x squared. Remember, when you have repeated linear factors, you write out each of those lower powers of the linear factor along with the current one. Then we have this irreducible quadratic x squared plus 1 as another factor in the denominator, so that numerator is going to be cx plus d. When we go through and recombine our template to match up the coefficients and form our system, we have the coefficients of x cubed combining to be a plus c equal to 0. The coefficients of x squared, we end up with b plus d is equal to 0. And the coefficients of x give us the equation a equals 1. And the constant terms give us the equation b equals 0. So this is now a 4x4 system. But the good news is that we have the values of a equal to 1 and b equals 0. And using this, we'll find that d is also equal to 0 and c is equal to -1. So our decomposition, as we have it written in our template, would be 1 over x plus 0 over x squared plus -1x plus 0 divided by x squared plus 1. Now, if we had reduced the rational function first, we would have ended up with 1 divided by x times the quantity x squared plus 1, and the decomposition would have given us 1 over x plus -1 over x squared plus 1. The exact same decomposition we got when we didn't reduce. But again, the decomposition will still remove the excess, but it is at a cost of solving a larger system of equations. So there's the trade-off. If you don't reduce these rational functions down, you may end up solving a larger system, and some of those values may indeed be 0. Thank you for your time and attention.